to our brief overview of arithmetic logic units, or ALUs, which are used in microprocessors and microcontrollers in great numbers. An ALU is a digital combinational logic circuit that can perform a wide variety of tasks, including the addition and subtraction we've discussed in previous sessions, and also logic operations such as NOR, XOR, and so on. The operands, or inputs to an ALU, are typically represent integers, and they are typically consisting of more than one signal or bit. In contrast, a floating point unit, or FPU, can perform arithmetic and other operations on floating point numbers and can handle fractions. ALUs can't handle fractions. This is a block diagram of a simple ALU in which we are choosing from multiple functions: subtract, subtraction or addition, and then some basic logic functions, AND, or XOR, or pass through, where we just buffer the input bits to the output and transfer them on their way. The selection of these functions is done using something called a multiplexer, which selects one of many to send to the output. In the multiplexer, the input bits A2, A1, and A0 will select one of 8 inputs to send to the output. Now in our ALU, we only have 6 possible functions or inputs here, so our last 2 possibilities will be don't cares because we'll never select those inputs. They'll be grounded or otherwise not used. So in this case, when we optimize the multiplexer, we can treat those outputs as don't cares, as long as we've carefully designed the circuit so that these 2 input combinations for A2, A1, and A0 never happen. The other 6 combinations are straightforward. For example, when A2, A1, and A0 are set to 0, 0, 1, then we've selected the AND function, and the AND of the 2 bits IA and IB gets transferred to the output, since we've selected the AND operation on those 2 bits. Likewise, when A2, A1, and A0 are 1, 0, 0, the 2 input bits IA and IB are just XORed together and transferred to the output. And likewise for the remaining 4 combinations. Multiplication can be done in an ALU using successive addition operations and shifting operations, and it makes a good case study in how we might do multiplication. In general, though, this straightforward method that models the way we learned multiplication in grade school is too cumbersome and requires too many logic gates, but it is the basis for how multiplication is done in ALUs. Now, when we did multiplication in grade school, we multiplied our top number successively by every digit in the bottom number, shifted them, and then added them together. So in this example, 1011 times 0 just gives us 0, 0, 0, 0, and we leave those digits in their original position. Next, we multiply 1011 times 1 and come up with 1011 shifted 1 position to the left, and so on and so forth through the 4 digits that represent our second number in the multiplication. Once we're done with the multiplication and the shifting, we can then add the results together using our existing add function in the ALU to come up with the result. Now, this has been a very brief introduction to what an ALU in a microprocessor or microcontroller might contain. In an ALU, we deal primarily with integer or logic operations and leave division and other more complex functions for the floating point unit. And in so doing, the ALU becomes a fundamental component of most central processing units, whether they be in full-blown microcontrollers used in computers or used in microprocessors for much smaller systems in one of our many electronic devices. ALUs are a critical component and are used in widespread in digital circuits. And that's all we have for ALUs today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.